Thank you very much. Okay, well, like Al was saying, this is the fourth installment of the Robots in Space series, and it's been quite phenomenal for me and for everybody in the club. I've traveled all over to give this series of lectures, and it's been a lot of fun, and it all started right here at McFarland. So let's go ahead and get started here tonight. Thanks for coming out for Robots in Space. Every year we talk about different missions that we've already talked about. 4 years ago we started with Sputnik, and we've worked our way through all of the different space missions over the last 60-something years. And the first thing that we do in all the subsequent Robots in Spaces is just catch you up, do a little update. So Voyager, it's been flying since 1976, has finally left the solar system again. About every 6 weeks or so, we get some sort of report or see an article somewhere that we know now Voyager has left the solar system. And that's because we really don't know what defines the solar system. You know, we have all these theories, we have all these postulates that there's a bow shock out there, there's a heliosheath and a terminal and a heliopause and all these different things at the edge of the solar system, but we really don't know what's there. That's why Voyager's on its way out of the solar system, or has left the solar system, as the case may be. But so what has happened this time is on July 7th, just a few days ago, Voyager 1 sent back information that said that a tsunami wave of high-energy charged particles hit the spacecraft.
I'm sorry, did you say highly charged or
high-energy charged particles.
Okay.
Mm-hmm. So Voyager's out there floating around in essentially soup of particles. It's past the influence of our sun. Our star no longer has any influence on the spacecraft. So it has particles from all kinds of other stars from all over the galaxy, and it's this background hiss, this gray noise. Well, when something happens in our sun that's significant, a coronal mass ejection, a solar flare, something of that nature, it knows how long it takes to get there, which right now is about 37 light hours. When it gets there, it can measure it, and it knows then that that's particles from our star. Right now, Voyager 1 is 127.77 AU away from the Sun. For those of you that don't remember right off the top of your head, an AU is roughly 93 million miles. 19.1 billion kilometers. So, I said that it recorded these particles, this tsunami wave, but it records it as sound. These here are the tsunamis. This is some form of solar expo, and this was the coronal mass ejection that hit it. So IC3, this is interesting. Has anyone seen any of the news about IC3 in the last week or so? I guess it's been. This is a really interesting spacecraft. It was the International Sun and Earth Explorer, launched in 1978. Totally successful mission, worked great, and in 1997 they tried to shut it down. And the shutdown commands didn't work, and the spacecraft started to tumble, so NASA just, closed the doors, locked the doors, and walked away from it, because they were done with it anyway. However, a rogue group of NASA scientists that have since retired from the organization got together and formed their own organization and called themselves the Satellite Hackers, and have regained control of this lost satellite. That's interesting. So July 3rd, it sent all these commands. It regained communication with the satellite, and 68 hydrazine burns. Now, hydrazine nozzles are these little itty-bitty nozzles all over the spacecraft that are attitude control, roll, pitch, yaw, things of that nature. And they're what keep a satellite, any space probe, stable. 68 hydrazine burns it took to get this thing back together. And then on the 8th, it sent one last set of commands to boost it into a stable orbit. And at that point, they were going to regain and start to do science with the spacecraft. Right. So the problem here is that the correction burns didn't work, and it's now on a collision course for the moon. So what has happened is hydrazine is stored in a fuel cell, like a gas tank. Next to that is a nitrogen tank, liquid nitrogen. And the two of them come together, react violently, and little tiny explosions, little spurts come out of the spacecraft through these jets. And they're what control the attitude, the direction of the spacecraft. that hydrogen has to be pumped into the system, the plumbing, if you will, and the pumps aren't working as what they've decided. So the hydrogen that was in the system and highly pressurized was able to move the spacecraft, allow them to regain communications and control, but they ran out of fuel that was caught in the system and did not get it boosted to the stable orbit. So if it's not corrected in time, it's going to crash to the moon on the 10th of August. The supermoon. All right, we'll have a lot to look at, right? However, the problem is they've lost control of the spacecraft. They can't communicate with it at all. So they are, of course, still trying, but they don't have much time to get it saved. So it was a nice try, though. It was a neat idea. You know, they came together to try to resurrect this old NASA throwaway stuff that still had plenty of fuel, plenty of power, and why not use it for, civilian science is what they call themselves. So, James Webb Space Telescope. Boy, we've talked about this a lot. It's the successor to the Hubble, sort of. It's not a visible light wavelength telescope, but it's going to bring a lot of science and certainly replace the science package that Hubble does. It is on schedule, finally, for a 2018 launch. It was originally supposed to launch in 2011. That was started in 1996. However, since it's been pushed back so many times for budget overruns and several other things, technical overruns, there's an independent organization, an independent audit, if you will, that says it's more likely to not launch until 2020, unfortunately. But as of right now, the official NASA word is that it's on schedule. Slightly over budget, only $8.335 billion over the original $500 million budget. Although not even close to the worst overrun in NASA history. That would have to be the space station. But in technical shape and scientific value, it's in top condition. All of the processes have gone properly. All of the testing is going fantastically. There's not been one major failure in any system or subsystem on the spacecraft since they started building it in 96. So these are the mirrors. These are 6 of the mirrors. There's 18 mirrors of gold-plated beryllium, hexagonal form. And these are in a vacuum chamber. This is a big vacuum chamber, a cryogenic chamber, actually at Goddard Space Flight Center in Greenbelt, Maryland. I just love the mirrors myself, so I threw several pictures of them in testing. This kind of gives you an idea of how big it is. 18 segments, 6.5 meter mirror. Hubble is a 2.4 meter mirror. So Hubble mirror is about this big. This one's 21 feet across. This is the back plane. Those of you that are telescope junkies yourself, you'll appreciate this one. The back plane has just been completed. This is the single largest cryogenically stable thing ever built by man. It's stable, so shrink swell as temperatures get hotter, things expand, colder they contract. This thing is stable to 34 nanometers across the width of the entire telescope, down to negative 400 Celsius. That's awesome. I had to look up, in all of the work we've done with this and talked about it, I did not know what the back frame was made out of. So I actually had to make some phone calls and look it up. And it is a extremely high-tech carbon impregnated titanium foam composite that has, what are they called? It's a new material, Invar fittings, all these little fittings here, which is a very special nickel and steel alloy, nickel iron alloy that is cryogenically stable. So, they're packing it up. We'll buzz through these since we're a little short on time tonight, but this is the back frame being packed up in its shipping container. Here it is ready. Here's a human for scale. It's ready to ship over the cryogenic testing facility at Goddard. Here is the heat shield. It is enormous. It's the size of a Bombardier, 792 jet plane. You can see the little person right there in the middle. It's bigger than a tennis court. So it's Mylar, super thin. Each one of these protects, I think it's something like 6 degrees cooler. So the back side of this is the sun side, and it protects, it's an infrared telescope, so it protects the front side from. So now we'll get to our mission here. This is the best images we have of Pluto from the Hubble Space Telescope. They're actually very computer enhanced. Essentially, it's to show that you can see lighter and darker, but that's the best we can do right now. And an actual image, I should have put one up, from Hubble, it's actually only 12 pixels. So there's a lot of artistic license with this image here, but this is considered the best that we have. And right now, still, even though New Horizons is so much closer, it still can't get better images than Hubble. But soon.
So 12 pixels total to find the whole circle?
Correct.
Wow.
Yeah. 12 pixels total. About 4 pixels across and not quite 3 pixels tall for the entire planet. So, since it's been changed to a minor planet, the official designation is Minor Planet 134340 Pluto. What's that?
He's called it 00001.
Well, but Pluto has been added to another class of planets that already had apparently 134,339 objects in it. So, highly eccentric orbit. Jim actually kind of parlayed me into this here. We talked about the moon's orbit. It's about 30,000 miles difference. 4.4 billion to 7.4 billion kilometers of eccentricity. That's 2 billion miles of eccentric orbit. So sometimes it's 2 billion miles closer to the sun. Sometimes it's 2 billion miles further away from the sun. And when New Horizons gets there, it will actually be closer to the sun, which is exciting because when it gets closer to the sun, some of the atmosphere, or it's the only time it has atmosphere, the ices that make up the planet, some of them sublet into an atmosphere, and that's what's going to make it interesting to study. Otherwise, we're just going to look at a big chunk of ice. So, you can see here, these are the orbits of the inner planets, and this crazy loop, here's Pluto. So, Plutonic year, 90,465 days, 90,100 days longer than an Earth year.
It's our days?
Our day is 365.
Oh, but see, you're talking about our days.
Right, Earth days. Right, this is 90,465 Earth days, Terran days, in a Plutonic year. Yeah. So 248 years. It takes 248 years for Pluto to go around the sun one time. Average surface temperature is 44 Kelvin. Let's think about that for a second. 1 degree Kelvin is a temperature in which all atomic movement stops. Atoms don't vibrate anymore at 1 Kelvin or at 0 Kelvin. It is only 44 degrees higher than that. It's about 380 degrees below zero. That's its average surface temperature on the planet. There we go. 7,294 kilometers around at the equator. Works out to about 5,000 miles. So if you were to fly from New York to Moscow, that's about how far it is around the equator of Pluto. So Pluto's not very big. It's about the size of North America, a little smaller than that. So you could safely say about the size of the United States. Pluto has a few moons, 5 of them in fact. We only knew of 1 moon in 1978 to 2004. 2005, 2 new moons were discovered. Nix and Hydra. So here we have Charon, Styx, Nix, Kerberos, and Hydra. Nix and Hydra were discovered in 2005 by the Hubble Space Telescope. In 2006, New Horizons, the spacecraft we're going to talk about tonight, left for Pluto. In 2012, we found 2 more moons. So we're finding all these new things, these new moons, and the closer we get to the system, we're going to start finding out what else is. In all other massive bodies in the solar system that have a large number of moons, there's rings. Anyway, so it is a hugely high possibility that Pluto has rings, which would make 6 planets in the solar system that have rings. And granted, Earth's ring is a man-made ring, but still, that's an overwhelming majority that have rings. So the more that we find out, the more it seems rings are actually the norm. Make for a great sunset, wouldn't it? So finding Pluto. There we go. There's Percival Lowell right there. Percival Lowell in the late 1800s, after the discovery of Neptune, was thinking that there should be another planet out there. Neptune's orbit was perturbed, and Planet X came up, and this idea of Planet X. And he searched for it for years. He funded the Lowell Observatory in Flagstaff to try to find this Planet X. And sadly, in 1916, he passed away, and the search for Planet X kind of stopped. There was other observatories around the world, other scientists that were looking for it. None of them were doing as good a job as Lowell Observatory was. So, in 1929, Clive Tombaugh was hired on. It's a fun story. He's a farm boy from Kansas. So, as a farm boy from Kansas, it's a lot of fun to know that Pluto was discovered by one of us. And he was all set to go to University of Kansas. And that year, there was drought. And there was no crops. His family couldn't afford to send him to university. So he built his own telescopes. He ground his own mirrors. He built his own telescopes. Now, I don't know enough of the story to answer my next question, but how did he know how to do that? That's what I want to know. Where did he get that information? You know, in the middle of a farm field in Kansas in 1929, that would have been pretty hard to come by, I imagine. But he did. And he drew sketches of the planets and of the moon and of everything he saw through the telescope. And he sent it to Dr. Sliver, the guy that took over for Percival Lowell at Lowell Observatory. And Sliver immediately sent for him so that he could start the search again for Planet X. In 1930, only 1 year, not even a full year later, he discovered Planet X. And it's a lot of fun. He walks into Dr. Sliver's office, having only looked for it for a year. He says, "Dr. Sliver, I have found your missing planet. I've found your Planet X." And after that, the name Pluto was actually chosen. Like a lot of things in astronomy, there was a contest, and one little girl who had suggested the name Pluto won, essentially. But Pluto was picked because of the PL initials of Percival Lowell. So here were the very first pictures. This picture here was taken on January 28th, and this one on February 16th. And you saw there in the image of Clive Tombaugh at the blink comparator, one eye on each picture. This little machine, you'd flip back and forth like the eye doctor. Is it A or is it B? Is it A or is it B? And he would watch these two images that were perfectly aligned, except this one little dot right here started to move. If you notice, that little dot is Pluto. It's on the left of these two stars in this image. But it's on the right in this image. So at that moment, he knew he'd found the ninth planet. So from 1930 to 1978, the most exciting thing that happened to Pluto was the discovery of Charon, its first moon. Its only moon that we knew of at the time. Unfortunately, some things have changed for Pluto, especially since 2006. There's been a little controversy. Roger and I have had a debate going for the last 5 years about whether it's a planet or not. I am a firm believer that Pluto is a planet, as well as the 271 scientists that work on the New Horizons mission. They would all agree. But what happened? Why is Pluto no longer a planet? I mean, everybody wants to know. Nobody knows really why. People ask me, and I say, well, it's politics. That's the short answer. The long answer is it wasn't alone. From 1930 to 2006, Pluto was a planet for only 76 years. Now let's think about that for a second. How long did I say a Plutonian year was? 248 years. Now these are Earth years, of course. Pluto wasn't even a planet for an entire Plutonian year, not even a third of a Plutonian year. It hadn't even made one revolution around the sun before we demoted it from being a planet. So, since 2006, Pluto has been defined as a few things. All of those, for one. There's a lot. I knew there was a lot. I had no idea how many there truly was. Dwarf planet, we know. Trans-Neptunian object, that makes perfect sense. It's past Neptune. We don't know what to call it. We'll just call it an object. Plutoid, fine. It's a massive round body out there in the outer solar system. Kuiper belt object. Pluto resides in the Kuiper belt object, or in the Kuiper belt. Fine. Plutino? I had to look it up. I had no idea. And let me tell you, I still have to shake my head. In astronomy, a Plutino is a trans-Neptunian object in 2-3 mean motion resonance with Neptune. For every 2 orbits that a Plutino makes, Neptune makes 3 orbits. Plutinos are named after Pluto, the first discovered object with this resonance. So nobody knows what to call it. Nobody knows how to categorize it. We just know now that it's not a planet. but we don't know what it really is. So everybody, all these different astronomers, all these different observatories, all these different organizations and institutions have different categorization for it. So it fits in so many things. It was a lot easier when we just called it a planet, right? But why? So this is Mike Brown here. He's an astronomer at Caltech. In 2005, he found the 10th planet. He calls his wife. He says, I just found a planet. I found the 10th planet. I'm going to be famous. He's famous. But not for finding the 10th planet. He's the man that killed Pluto. He's now written a book, The Man Who Killed Pluto. He accepts it. It's his fate. The problem was, the 10th planet, Eris, is bigger than Pluto. Pluto is no longer this lonely little ice ball out there in the Kuiper belt floating around. It's now one of many, many objects. So, do we call those planets? I vote yes. I like the idea of having more planets. But nobody knew what to do. And so not only is it larger, the same year 2 more things were found. Makemake and Haumea. 2 more planets. And at the time, everybody was scrambling because planet, root planetae, ancient Greek, for wanderer in the sky. Once upon a time, the sun was a planet. The moon was a planet. And slowly over the years, the definition of planet has changed, but never officially. So this finally made the IAU, the International Astronomical Union, vote to place Pluto in a different category. They took away its planethood.
Those who are in favor of Resolution 6A, which introduces this new category of trans-Neptunian objects with Pluto as a prototype.
The recommendation is that we consider Pluto and other similar trans-Neptunian objects to be in a special class.
I have the weirdest collection of random video clips. Who else has the official death of Pluto? So the new definition, what is the new definition of planet? A planet is a body that orbits the sun. It's massive enough to achieve hydraulic equilibrium, hydrostatic equilibrium even. What does that mean? It means it's round. It means it's a sphere. And it's cleared its neighborhood of smaller objects. So the Earth, in its orbit, is empty. For the most part. There's other stuff there, but again, that's another debatable subject. Pluto is one of many and many and many of these objects, and in fact, some of them are larger. Eris is 27% heavier and denser than Pluto. So it could no longer be a single planet. I say it's a planet. Here's some of those objects. So look here, Eris is just a tiny bit bigger, but it's much, much more massive. And Charon, the moon, the biggest moon of Pluto, almost as big as Pluto itself. So a lot of these are being found out there that they could be categorized as binary systems. 2 planets orbiting a barycenter, a equal gravitational center between the 2 of them. There we go. I've seen all kinds of estimates. Mike Brown himself has published a list, Mike Brown being the astronomer that discovered Eris. He's published a list of 360 found objects that fit the category of dwarf planet the size of Pluto. That's cool. That's a lot of planets in the solar system. Alan Stern, who is the principal investigator for the New Horizons spacecraft, I've listened to a talk of his. I've been to a lecture where he said he believes there's more than 1,500. That's a lot of neat stuff to go try to explore now. For a guy that wants to build robots to go into space to do the exploration, the future looks bright. Minor planets. Now, minor planets gets a little fuzzy. Asteroids are minor planets. But there's 600,000, over 600,000 minor planets that are registered by the Minor Planet Group, think tank, that are large enough to explore. That give us reason enough to know they're there. Over 600,000. Joe? I could do an entire hour lecture just on that.
Well, does that mean that the minor planets aren't round?
No, Pluto's a minor planet. Exactly. I looked for days to try to clarify it, not because I needed it for this lecture, but just because I wanted to try to get it straight in my head. And my head's a spaghetti bowl right now trying to figure out how they all fit together.
The harder you tried, it got worse.
It really did, yeah. You know, I've found over 24 different categorizations for all of the same thing, with a slight variance somewhere. Well,
One thing I should mention is that for several decades after Pluto was discovered, it was believed to be very much bigger than it actually is.
oh, absolutely. They thought it was perturbing the orbit of
If they
Neptune.
had realized its size, things might have been a little different. But they, for the next 20, 30, 40 years, they thought it was hugely bigger than it actually is.
Right.
And I noticed when I was a kid in grade school, they said it was so big, and when I got to high school, it shrunk a little bit more. And then as you get older, it gets littler, and you go, well, why this thing is only a small fraction of what they said it was 40 years ago?
But I don't care how big it is, I still want to go explore it. And that's the point. And we will in a year. So this is a quick representation of those 600 objects.
Where did that come from, that diagram?
Right off the top of my head, I don't know, but I've got the information. I give it to you afterwards. If you want.
I'm just curious, was it like a magazine on the internet? Or?
It's out of a journal, yeah. But I don't have off the top of my head which one it is. Yeah, it's a peer-reviewed piece. Yeah. So it actually came from one of the NASA database pages of journals. So now, getting to Pluto. See how we do it.
Three, 2, 1. We have ignition and liftoff of NASA's New Horizons spacecraft on a decade-long voyage to visit the planet Pluto and then beyond.
So as of today, we're 2.97 AU from Pluto. We're almost there. July 14th of next year, we'll be on site. We'll be at the planet.
And then we'll get good pictures.
Boy, we'll get good pictures. And that leads me to some really fun things. I said that the best picture that Hubble has right now is only 12 pixels. And the best picture that New Horizons has, mind you, a much smaller camera, or bigger camera, more pixels, but much smaller telescope. It's still not as good as that Hubble picture. And they have the literal date on the schedule. It's called Better Than Hubble. When we reach the point where we're starting to obtain data better than Hubble, that's when it starts to come home. That will be the day, I've got goosebumps talking about it, that will be the day, in about April of next year, that everybody, Joe?
Do they have an estimated density for Pluto?
They do. I don't have that information in here. It gets a little, forgive the pun, it gets a little dense to talk about mean densities and things of that of planets we can't see more than 12 pixels of. So, but that's why this is exit 9. We've just passed Neptune. We're almost there. 3 AU, just under 3 AU now. So there she is, New Horizons. That's the spacecraft that'll get us there. This is in the software. Let's see. This is at APL at Goddard. Here's just a little animation of it on its journey, pretty lonely journey out there in the far outer solar systems. Let's talk about spacecraft. It's a New Frontiers class spacecraft. Now, what is New Frontier? It's the very first one of the New Frontiers. So nobody knows what New Frontiers actually means, and that's why the talk tonight is called Pluto: The New Frontier. So there's discovery missions. I think everybody knows what they are basically, but they're fundamental in budget. $0 to $496 million. A discovery mission is the proposals that we wrote last year for our mission to Mars was a discovery mission. That's my research, was a discovery mission to Mars. So they're a little bigger than Discovery. They're from $500 million to $2 billion missions. And then the flagship class are $2 billion to $3 billion. Then you've got the International Space Station, which is obviously a flagship, and the James Webb, which is almost $9 billion. That's clearly more than 3. That kind of gets into a fuzzy area, what they call those. But that's how the hierarchy. There's Explorer missions, which range in there as well. Explorers have been going along since 1958, been around a long time. The spacecraft is built by the Applied Physics Laboratory at Johns Hopkins University in cooperation with the Southwest Research Institute. And Alan Stern, who I've mentioned several times, is at Southwest, is the principal investigator for the mission. And he actually left a position as the associate administrator of NASA to be able to finish fulfilling this. And he's been pegged several times by the Obama administration as a new director, but he won't take it because this is his baby. Now, think about something. It left in 2006, 2 months before the IAU canned Pluto as a planet. I guarantee you, I've heard him say it 100 times, Pluto's a planet. And he won't back down from that. His mission is going to a planet, not to a dwarf. It was launched the 19th of January 2006 on a 9.5-year primary mission. Now that's the mission to Pluto. So anything beyond that is gravy, as long as we get to Pluto. There were some setbacks and some trials to get there, but we're on our way. So the secondary mission is to study what else is out there behind. And actually the Giant Magellan Telescope right now, the Hubble, the Keck, all of these huge earthbound telescopes, including the Hubble Spacebound Telescope, are looking to find what's on the trajectory to go to. We now think there's 600 of these objects out there. There's bound to be some close enough that we can do some trajectory changes and make it to a second one or a third one or maybe even a fourth and fifth one. It's going to be an interstellar spacecraft. It's only the fourth ever to do that. Obviously, we have the 2 Pioneers and the 2 Voyagers. It will be an interstellar spacecraft. It's just hopefully going to catch some fun stuff along the way. It's the fastest launched spacecraft from the Earth ever, of anything ever launched from the Earth, of an escape velocity of 36,373 miles an hour. Escape velocity is 25,000 miles an hour. Space shuttle leaves at 25,000 miles an hour. The moon shots were 25,000 miles an hour. All the Apollos were 25,000 miles an hour. This craft left at 36,373 miles an hour. And that's not fast enough. It was launched directly, the first time ever, into a Earth and Sun escape orbit. If you guys remember, the Voyagers had to go to the inner solar system for a gravity shot to gain enough speed to get out there. But this was launched directly into a solar escape trajectory. Wait till you see the rocket they had used to do it. It swung by Jupiter and gained another 24 miles an hour in a gravity shot. It's now traveling at 54,497 miles an hour. The fastest spacecraft, faster than Voyager. Either Voyager. The only other spacecraft, the only other human-made object that's ever traveled faster, technically, was one of the Helios spacecraft. There's 2 of them. They dove them into the sun. On their way into the sun, the gravitational influence of the sun made them travel faster. But that was non-human influenced. So this is by far the fastest moving human object ever. So, after launch, it went by the moon, then it went by Jupiter. How long did it take the Apollo crafts to reach the moon? Anybody that knows, just shout it out. 3 days. That's how fast it's moving. Made it from the Earth to the moon, 246,000 miles in 9 hours. How long did it take the Voyager to get to Jupiter? Anybody remember? 3.5 years. It made it to Jupiter in 13 months. That's less than the time we're planning to put people on Mars. 13 months. Yet the solar system is so big and the outer solar system is so vast, it still takes 9.5 years to make it all the way to Pluto.
Could I ask you a question?
Yes.
I totally didn't understand what you meant about putting people on Mars and comparing it to the time it takes to get
To get a spacecraft to Mars is 8 months. To get a human spacecraft to Mars.
That would be the time to send a person from Earth to Mars.
Right. Just to Mars would be 8 months. Right. So, and then to get them home would be another 8 months. And it made it all the way to Jupiter in that time. Paul?
Well, I was just wondering, if this thing is zipping along so fast, is it going to be zipping by Pluto so fast that you can zip a couple pictures?
Yeah, Pluto's a tiny planet, but it's still a huge object.
Yeah.
And it has the highest resolution imager ever put on a spacecraft on it.
Okay, well, it needs
It will. The last information I have is we're looking at something like 30 million images of the planet is expected to return. Yeah, so we'll have plenty of data to sort through. So the rocket, I told you, I said wait till you see the rocket.
That's going to be about like passing a town of 4 houses and saying, oops, you missed it.
Oh, I don't think we're going to miss it. So an Atlas V, huge rocket by itself, normal launch capacity, big rocket. Normally they have 2 or 3, well actually most satellite missions use 0 solid rocket boosters. Some use 2. Huge missions use 3. There's your rocket right there with your solid rocket boosters, your normal 2 on a V5. The 551 is a very specific designation. It's the only one that's ever launched. It's the only one that's ever had a third stage. It used 5 solid rocket boosters. So you've got 5 solid rocket boosters. These are the same solid rocket boosters from the space shuttle. You have 5 solid rocket boosters and a third stage. There's no wonder it left at 37,000 miles an hour.
And you're going to have to be pretty careful about overheating in the atmosphere with gasoline boosters.
Well, with third stage, you're going to, the higher in the atmosphere you get, the less need you have to worry about the density of the atmosphere with overheating. So that's the reason for the third stage. It was the first time ever they used a third stage. And they used a big one, a 48B. That's a big third stage. 2 million pounds of thrust at takeoff.
What kind of G's?
I have no idea.
Probably not something you want to experience.
Probably not survivable, would be my guess. I mean, the space shuttle, your 9 to 11 Gs, 11 is really, really, really pushing it. That's at 11 million pounds of boost. This guy only had an 1,100 pound payload. That's a lot of thrust under a little empty box. But we needed it. Otherwise, it would have taken 33 years to get to Pluto. I mean, just a few years ago, Voyager passed the orbit of Pluto. And it was launched in 77, September 5th, 77. Because it was moving so fast, even the third stage is on heliocentric escape orbit, or velocity. So it's not on a Plutonian trajectory because it didn't do the Jupiter system gravity test. So it's on a totally different trajectory. But it also will leave our solar system. our first intersolar space junk. So, power system. How does this thing power? This is an RTG right here. A radioisotope thermoelectric generator. Nuclear. Many spacecrafts have been nuclear. They've run, RTGs. And a lot of people ask me, how do they work? What do they do? Well, it's the first time we're actually really delve into an RTG. It's extremely safe. They've been tested many times. Many spacecraft. Caveat. The U.S. versions are very, very safe. The Russian versions, not so much. They've sprinkled americium across Russia a couple of times and polonium once, but ours are very safe. Specifically, these GPHS units are what they call second generation or new generation. So even though new generations have been used since Galileo, they're the important ones. There we go. So it runs on 11 kilograms, 24 pounds of plutonium. Plutonium-238 oxide, much different than plutonium-235. Believe it or not, plutonium being the most toxic element on the planet, plutonium-235, not as nasty as plutonium-238. However, the advantage is plutonium-238 only has an 87-year half-life. So it gives all of its energy in a very short amount of time, where plutonium-235 has a much longer half-life, but not as reactive. But that's why we use it. There's a slug of it right there, a nice glowing red-hot ember of plutonium. It's in a ceramic shell. And this right here is the thermocouple. It's a Peltier device. Unfortunately, I was going to bring one tonight. I just did not have the time with the technical difficulties we've had. But this directly turns heat energy into electricity. So that's how it works. This big core of nuclear material gets really hot, heats up these things, and it puts out electricity.
Can you give an estimate about how big the thermocouple is in inches?
2 inches by 2 inches, basically 50 millimeters square. 50 millimeters square. I had some. I was going to bring tonight, but unfortunately I didn't have a chance. I was going to actually pass it around to everybody and let them hold it and watch a meter go up. But nonetheless, this is what they look like. So yeah, it's about that big. Here's a little animation I put together to show you exactly how this stuff works. This is an RTG. This happens to be an MMRTG. This is the one off of the Curiosity rover. MM just is multi-mission. That's all. So within this here, we have these thermocouples. Inside this tube is going to be your heat source, and we'll get to that in a minute. We'll get inside the tube. Radiators, obviously, to lose heat. On a lot of spacecraft, we can direct that heat into the spacecraft to keep it warm. Space is a cold place. This gives us everything we need: heat, energy, everything we need. So these thermocouples then send out, they go into these bridges here, these banks, and they send the power into the spacecraft. Here's our heat source here, the GPHS, the general purpose heat source. This is important that it's a GPHS. That's the next generation radioisotope thermal generator. It's safe, super safe. They've blown these things up. They've done everything they can to them, testing them to show for catastrophic explosion of the spacecraft on the launch pad, in orbit, above orbit, in the atmosphere, re-entering the atmosphere, on the ground. Survived everything, many, many times. In fact, these units are the predecessor to these units, but the same sort of design was used on the Apollo missions. Apollo 13 crashed back into the Tonga Trench. This thing survived all the way in. 2 of them, 2 American crashes. Both times the predecessor to the GPHS, the SNAP 14s, survived completely unscathed. Survived falling from space, hitting the ground, and surviving. So they're pretty safe. Let's look inside it. Here's your little plutonium slugs here you saw a minute ago. There's 4 in each GPHS. Inside, or around those plutonium slugs, is an iridium heat shield. It's a case. Keeps the heat in, heats up, uses it for transport. It's also protective. Those caps come together, and you'll see an animation in a minute, and go inside this graphite impact shield, or this tube, this shell. That graphite itself is extremely well versed for being around nuclear material. A lot of graphite in nuclear reactors and things of that nature. It's very absorbent. That then goes inside a carbon fiber sleeve, a ballistic carbon fiber sleeve. All of this then goes together. This one actually comes in the back like this, where this one here comes in the front. They go side by side into an aeroshell. For those of you that have been to many of my lectures, aeroshell simply means can fall from space into atmosphere. An aeroshell is specifically designed to go through an atmosphere and safely land on the ground. Maybe. Here we go. So all this goes together inside the graphite shell and inside the carbon shell. Then you stack 8 of these together. Now I've got a picture looking down inside of a working one of these, and I couldn't find it at go time here, so I have to apologize for that. It's a neat picture. A little creepy, but pretty cool. So here it gets hot. These thermocouples pick up the electricity and send it out to the spacecraft.
Say how much each module has
Yeah.
power.
Yep, we'll get to that. So here's our RTG we were talking about. So why do we need an RTG? And we'll get to your question here in a minute. There's only 1/1000th the amount of light at Pluto that there is here at the Earth. Solar arrays, useless. They wouldn't do anything at all. Now, one of the interesting things about these RTGs is the best thermocouple that's ever been recorded as far as efficiency is just under 7% efficient. Just under 7%. 3 to 7%, I don't know the exact unit for the particular RTG that's used on the New Horizons spacecraft, but it's less than 7%. So a lot of wasted energy, but we've got energy for a long time. So solar panels wouldn't do any good at all. They wouldn't do us anything. The unit on New Horizons, this guy here, will only produce about 200 watts of energy at the encounter because it was stored for 21 years. Now, there's a lot of weight, a lot of time that deployment slipped of the spacecraft, and there was a shortage. There still is a shortage today. They've finally redone production for spacecraft use, and they're finally starting to make the plutonium-238 again. It's just happened within the last few months. But there's such a shortage of it, the Department of Energy had to literally scrape some up out of a back shelf somewhere. And I think it was Hanford had to come up with some, and Los Alamos had to come up with some. And all of these government organizations that literally just had some hanging out in the back room had to scrape it together to have enough power to send New Horizons out. A lot of it had sat on the shelf for years and years. I told you the half-life of plutonium-238 is only 87 years. So 21 years worth of this material sitting, that's a quarter of the life of the output. They decay over time. So I believe it was 321 watts or something like that, or 280 watts that were available when it left Earth. Only about 200 watts that are available when it gets there. The spacecraft requires 190 watts to do its primary mission, which is Pluto. Once past Pluto, the secondary mission isn't going to require as much power because there won't be as much information needed as far as atmospheric stuff, and you'll see the battery of instruments that are on this spacecraft. We won't need to do that much, the other planets, as opposed to Pluto. Pluto, again, is the primary mission. Here's the instrumentation. Here's your spacecraft. You see the RTG out here, communications disk. This is a fun little one right here. That's the important one that Joe was asking about earlier. So Ralph. We've lost some of the acronyms in these. I don't know where they got Ralph. It's not an acronym. It's a visible and infrared imager. And it's to take color and composition pictures and thermal mapping of the planet. Alice is ultraviolet. It does spectrometer of the atmosphere. The light coming from the planet, the light coming from the sun, the difference between the two, lets you know what elements are on the planet. So it's an atmospheric composition analyzer. Now we're into some acronyms. REX, which stands for Radio Science Experiment. It's also the high gain antenna, the communications dish back to Earth. So REX is actually this little guy here. And then the big dish is the high gain communication antenna. And it communicates directly to the Deep Space Network. And the spectrometer in here is atmospheric composition and temperature gradients as well. So, Pepsi, which I enjoy. That's a fun one. The Pluto Energetic Particle Spectrometer Science Investigation. They were stretching here to make the acronym work, but I like it. They made it work. That's fine. High energy charged particles, atmospheric particles, anything around the planet. We want to know what's there. If the atmosphere is so thin, the gravity is so low, it's going to lose some of that atmosphere. The solar wind itself is going to affect that atmosphere, and we want to know how, why, what's it doing. To escape me in the atmosphere. That's the short story. That acronym must have been hard work. Solar wind, just like I was talking about. We want to know how the solar wind interacts with Pluto's atmosphere and how Pluto's atmosphere interacts with the solar wind, the high energy charged particles that the sun puts out that make it all. LORRI. That's the one. That's the you're not going to miss the little town, Joe, right there. LORRI, the long range reconnaissance imager. The neat thing about LORRI is it can pick Pluto up from a long way away. Not quite as far away as 3AU. That's a long way. But we'll start doing imaging. The better than Hubble date is next April. From that day forward, data just flushing back. Next April. So in 3 months from the better than Hubble date, we'll be at Pluto. So 3 months of every day better pictures. That'll be a Facebook page to watch. Every day better pictures. You know, I've sit there at 3 o'clock in the morning when Jim has been imaging Pluto. And then 3 days later, when we have to image again, to see the dot move, because that's all you can see is a dot move. It's going to be neat to see that dot up close. High resolution, like I said, is the highest resolution imager of any spacecraft. But not a very big aperture. The SDC is kind of a neat deal. It's a student dust counter. It's an experiment designed by students, built by students, and run by students. High school students, not college. It's neat. Space dust, junk, stuff, particles, anything it can get its hands on. That's what it does. So, some neat things on the spacecraft. In 97, Clive Tombaugh passed away. Sadly, he won't get to see our journey there. 25 grams, almost an ounce is 28 grams, of his ashes are on the spacecraft. On the way to Pluto. Because it was a planet when it left. I don't know why this means so much to me. It's a big part of the craft to me. I have no idea why we did this. I know on Voyager we did the golden discs. I get that. Creepy, but I get that. We have a CD with 434,000 some odd names of people on the planet on the spacecraft. Because aliens have CD players. But I suppose if they do, that might end up as a shopping list. Piece of Spaceship One.
How much does it cost to get your name on it?
I know nothing about the names that are on it. I don't know. But if I was a hungry alien traveling around and bumped into this thing, it might look like a menu. Spaceship One. Spaceship One was built by Burt Rutan and Scaled Composites out in California. And several years ago, it was the first civilian object to go into space, the first civilian spaceship. And they're now, of course, on Spaceship Two, White Knight 2, Mothership 2. But a piece of, and I unfortunately don't know what piece, but a piece of the first civilian spaceship is on board New Horizons. Memorabilia. It's just a piece. It's along for the ride, I guess. It's memorabilia. I mean, it's to dedicate, something to humanity's foray into space, our climb to the heavens. There's an American flag there. I'm hoping a very small one. A lot of weight, right? Florida State Quarter officially has a trim weight. I don't know why the others aren't a weight. They clearly have to take into consideration the weight of the ashes and the flag and the CD on the spacecraft. But officially, that quarter is bolted to the spacecraft as a trim weight. So thank you for coming to Robots in Space 4 and listening to Pluto and working through all of our technical difficulties here tonight. My favorite part of this is, of course, the questions and answers. So if you have any questions, I'd be glad to field some. Roger, you always have good questions.
I'm speechless. I was overwhelmed with all the information you provided. Those animations and those really obscure pictures. It must take a long time to collect all that stuff.
It does.
I guess my only question is, when and where will you give this talk again so that I can absorb a little more of it?
It'll be online in a few days on YouTube. All of the Robots in Space are on YouTube. Mm-hmm.
Because Jim's videoing?
It's being videoed right now, yeah.
But you don't have another live presentation?
I don't right now because my summer has been off because of my expedition in Wyoming. And usually the next stop is a resort.
When did you find out? Because I think a lot of people might tell their friends, hey, this is something.
Yeah, well, it will definitely be posted on the club's page and Facebook and stuff. So, all right. Well, if there's no other questions.
Thank you.
Thank you very much.